तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, having seen the techniques for reduction of Boolean functions by Boolean algebra as well as by using corner maps, we said we should use it in real circuit design. That is where the object is. The object of this exercise, the program or the course, as well as in real life in terms of digital design. The object is to design circuits which work according to specifications given. So, we will look at a few circuits which are generally used in digital, just tell you how to translate a specification into a truth table and how to translate the truth table into a design using the corner map. I said there are two types of circuits in the beginning. If you remember, there are two types of digital circuits. One is called combinational circuits. A combinational circuit means the circuits which are whose outputs depend on the inputs at the present time. The output depends on the inputs. The input changes, the output correspondingly change. There is another class of circuits called sequential circuits. It is also the output depends on the input, but not only on the inputs, also on the previous behavior of the circuit. That means the output of the sequence circuit depend on the present inputs as well as the past outputs. So, the techniques we have learned so far, the graph method and the Boolean algebra, etc., we will use for designing first combinational circuits. Some of these generally used commonly used digital circuits. One class of circuits, so we will call this topic design of combinational logic. Circuit. One class of circuits in combinational logic is called a code converter. See, we represent data using codes, all of us know that. A simple binary representation of a digital number, decimal number, is also a code, because I have only two symbols in binary 0 and 1. I need to represent a number which is larger than 1. I need to use same 0 and 1 different patterns. Is that right? That is a code. So, for example, 5 is written as 101. Coding of the binary number into decimal number, we call it conversion. decimal to binary conversion, but basically it is a code that represents a given binary decimal number. Think of alphabets, you write letters using computers, you send emails, you send SMS, right, using cell phones. These are alphabets and special symbols, characters. Again the computer can only realize these are switches, as I said, all the circuits inside are basically logic gates. The last class I told you how logic gates can be used for arithmetic operation. These are the ones that are used for decision making, these are the ones that are used for control. All of them finally boil down to AND OR inverter. I told you in the beginning, AND OR inverter are fundamental blocks, fundamental gates by which you can design any circuit, and I also said that can be even replaced by a whole set of NAND gates or NOR gates, which are called universal gates. So that means when I have an English alphabet or any alphabet for that matter, you want to represent with a computer, you want to store it and process it and output it. You need to represent these symbols of English characters or numerals or special symbols or punctuation marks by means of codes. A well known code for representing alphabets is called Ascii code. Have you heard of this? Ascii? Ascii stands for what? American Standard Code for Information Interchange. So anything is a code, any representation of binary pattern to represent a given data, be it a decimal number, be it a large number, be it a text, be it a graphics also sometimes, even graphics are represented as binary numbers finally. A television image you see or light intensity, but light intensity has to be represented as the intensity levels. The intensity levels are translated as binary numbers. A larger binary number will be having a more intensity. Larger intensity will be represented by a larger binary number. A lower intensity point will be represented by a smaller binary number. So one class of circuits which are very commonly used, very standard, are these code converters. Sometimes you want to convert from one type of code to other type of code. Sometimes for convenience, sometimes for security reasons. You may want to have a code and you don't want somebody to understand, so you have a key and only you know the key. So you have to convert your numbers using that key to another set of numbers and use it. Only those people who are authorized know that number, will know the key, rest of them will not. So that is one reason why you want to convert one type of codes, a number represented in one code to a set of numbers represented in another code. Code conversion is required for many reasons. As I said, one is for security reasons. Then we may also want to do it for some hardware reasons. Sometimes by having a particular representation of zeros and ones in a particular pattern, particular way, the patterns of zeros and ones in a number, if they are in a particular way, it falls into a particular pattern, the hardware implementation becomes simpler. We will see more of it later on. The class of codes which fall under this category for simplification of hardware, one is called the XS3 code, the other is called a gray code. XS3 code is a code which is used to convert a number, a set of numbers to another set of numbers. By this XS3 code, a particular operation of arithmetic operation becomes easier. One operation called complementing operation, 9th complement they say. We will see it later on when we talk about arithmetic circuits. So complementing of these numbers becomes easier if you represent those numbers by in XS3 codes. That is the reason why we want to go for XS3 codes. There is no secret there. You have a decimal number, a binary number, decimal numbers represented in binary form. Before you operate these numbers, before you use these numbers in arithmetic operation, you convert them into XS3 codes and you do this and then get it back into the binary code, because the hardware for particular operations will be easier, simpler if you do XS3 coding. Same way with gray code. Gray code is used for reducing the switching activity, they call it. Anytime you change a number from one code to another number code, so zeros have to be changed to 1, 1 to become 0. So suppose I have a code, number changes from, suppose I have a number 0 1 1 1, I have a 4-bit number with 4 binary digits with a 0 MSB 0 1 1 1, that is 7. 0 1 1 1 is a 4-bit representation of a 7, number 7 decimal. Number 8 decimal is 1 0 0 0. Suppose I switch from, so I keep counting, let us say, count from 0 to 1 2 3 4 5 6 7, it is indicated, 7 is indicated by 0 1 1 1, and next count is 8 1 0 0 0. Now all the 4 positions, binary digits have to be changed from the previous values. First one has to become a 0, second one has to become 0, third one has to become 0, fourth 0 has to become 1. This is called switching, changing of the value of the binary from one value to the other value is a switching, we have to change its value. As I said, it is a switching. Why did I say it is switching? Because we represented binary operation by a switch. A closed switch is a 1 and a open switch is 0. So a switch has to be opened to make a 1 a 0, a switch has to be closed to make a 0 into a 1. So 4 switches have to be closed or opened, 4 switches have to be operated when I want to change a number from 7 to 8. Suppose I need to switch only one switch at a time. Whatever is the magnitude, whatever be the magnitude of the number, from one number to the next number, if I have to make only one switching, that reduces some activity. Switching activity represents speed of operation, switching activity represents power consumption. These are the things which you have to take from me now, but you can think of intuitively. It is not, you have to close and open more switches, more energy is required, and it is going to be less fast, is it not? So when I say power saving and speed improvement is possible by having a gray code representation. So in certain operations where this is important, switching speed and power saving is important, there also hardware minimization also may become an important feature. That may be reason. So the reasons may be many. Code conversion is a standard operation in digital systems. Why it is done, as I said, may be many reasons. Many reasons may be given for this. One is for security reasons. Only you know the conversion. Nobody else knows the conversion. That may be good enough reason. Called encryption. Cryptography, they heard of cryptography, secret documents. Then the second reason, as I said, is to reduce the hardware. Some operations are possible with XS3 codes easier by reduced hardware than by normal binary representation of decimal number. So decimal number have to be operated using computer or calculator or any digital circuit. I cannot feed the decimal number directly, I have to convert it into binary and feed it. When I directly feed it as a binary number, it requires certain hardware. When I convert them to XS3 and feed it, I find certain operations are easier. Certain operations require less hardware or less logic. That may be the reason for coding, XS3 as an example. The third one is the switching activity and power saving and all that speed activity. That is the gray code. These are only some examples I am giving you, a few examples. A representation of a number using zeros and ones need not follow the sequence which are used to. 0 is 0, 1 is 1, 2 is 1 0, 3 is 1 1, 4 is 1 0 0, 5 is 1 0 1. This is called natural binary sequence, normal binary sequence. Do not say that when I am using a computer always you to follow the natural binary sequence. It is not necessary that you have to use a natural binary sequence for inputting numbers into a computer or any digital hardware. Into any digital hardware you can have a coded number, perform the operation in the code using in the converter code, get the result in the converter code and reconvert it back to binary number with which we are familiar. So that is why I am thought I will give you some examples of code conversion. How to design a code converter is the topic today. Combination logic, I want to give you practical circuits. I told you last time we only talked about techniques using all arbitrary sum of product and product of some functions. I gave you min terms and max term which were random, whatever I thought was, whatever came to my mind I just gave as a example. But in a digital system design you have to start with a specification for a purpose. So in order to get you to that mode of thinking, we will have to take some examples of practical circuits, and one such practical circuit, a class of circuits, is the code conversion, and I gave you a simple example of coding, what a coding is, be it binary to decimal to binary code, ASCII to character to ASCII codes, or any of these XS3 or Gray code, whatever it is, these are the various codes. And we will now first take an example of how to convert decimal to XS3 converter. XS3 is nothing but add 3 as name suggests. If I give you 0, you make it into 3. If I give 1, make it into 4. If I give 9, make it into 12. That is all. Only 0 to 9 is required, in a decimal system. We will deal with this digit by digit. There are two ways of handling decimal numbers in a computer or in a calculator. I can convert the whole number into binary and have series of ones and zeros, mind boggling, or I can take digit by digit, convert them into binary and work on each individual digit and put them together finally. So when I consider each digit, decimal digit, as one unit, then each of those units will have 4 binary bits, right, 4 bits. But out of 4 bits I can have 16 combinations, but we are only interested in 10 combinations, 0 to 9, other 6 are not required, not used. So the given code, binary code, I will call it B0, B1, B2, B3 are the 4 binary bits of the binary code, and the XS3 code, corresponding XS3 code, I will call it E0, E1, E2, E3. All of you know that this is called the least significant bit, or LSB to the right. The one to the left is called most significant bit, or MSB, because the value of this bit is much higher compared to this. This is the minimum value, this is the next higher, next higher, next higher. So LSB to MSB there are 4 bits, here also LSB to MSB there are 4 bits. So I am only interested in 9 of these, 10 of these bits, 10 of these values. Zero to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal, written in binary form, 10 variations, 10 values or 10 patterns, and corresponding XS3 is all I have to do is to add 3 and then convert it back to binary. That means 0 is represented as 3, 1 is represented as 4, 2 as 5, 3 as 6, 4 as 7, 5 as 8, 6 as 9, 7 as 10, 8 as 11, 9 as 12. If when you are doing this converter, so what we are going to design is a converter binary to XS3 converter, in which I will give B0, B1, B2, B3 as inputs, get E0, E1, E2, E3 as outputs. Strictly speaking, I should not even call it binary. It is binary means it is a natural binary, it can go from 0 to infinity, any value, higher value. But I am going to restrict from 0 to 9 binary. That means I am going to have only decimal representation, decimal numbers, but represented as binary digits. Decimal number 0 to 9 is my interest, but I cannot handle 0, 1, 2, 3, 4 etc. in a computer. I need only zeros and ones into my computer. So I convert my 0 to 9 into binary bits or bits, not binary bits is a redundant way of saying, binary bit means binary digit. Since I am converting 0 to 9 into bits, so actually strictly speaking I should not even call this binary to XS3 converter, I should call it BCD to XS3 converter. Already there is a coding, binary coded decimal, actually these are decimal numbers represented as binary codes. So I will call it BCD to decimal converter. So BCD number will be and XS3 number. So if B0, B1, B2, B3, B0, B1, B2, B3 have no possibility of getting values beyond this, but since we are having 4 inputs, this is a 4 input, I have 16 values in the truth table, I will have a corner map with 16 cells, I do minimization etc. I can conveniently use them as don't care condition. Do you remember the don't care I talked about? So if anything happens from here on, the last 6 entries corresponding to 11, 12, 10, 11, 12, 13, 14, 15, all these 6 entries the output will be what? Don't cares. I do not care about these outputs because these inputs are not going to come, but I can use this to my advantage for simplification. We talked about it in the last lecture. Now my problem is stated, this is how your design should start. Clear statement of the problem, if possible by a representation like this, schematic, followed by a truth table, then you do the Carter map, do the simplification, draw the logic circuit. Then go to the lab, get those gates, wire it up, test it. That part we will do in the practical part of this course. There is a lab attached to this course which we will do later on. So now we will have to take each of these values E0, E1, E2, E3 and find out these logic combinations or logic function which can represent E0 in terms of B0, B1, B2, B3, E1 in terms of B0, B1, B2, B3 etc. We will have to write 4 functions. We have to write what is E0, f of, we will have to represent E0, E1, E2, E3 as functions of B0, B1, B2, B3. Is it not? That is our job. Once we have this function in simplified to minimum form, then I know how to proceed because I can buy those gates and put it together and then get the circuit to work. Let us quickly do this. We will first draw the corner map for B0, E0, K map for E0, this is B2, B3, B2, B1, B0, now you have to this is the values, all the 16 values are here, the corresponding E values are here. So I have to put these E values into this map. It is a 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Beyond that all don't cares. Only 10 entries are there, all others are don't care conditions. So I put a X here. Do you understand why I did this? This is the function I want to represent. This is f of E0 is f of B0, B1, B2, B3, f1 of or f0 of. That means these are the inputs, and for each input this is the output truth table. Like that I have to do for each of these outputs. For this output I should draw a corner map, for this I should draw a corner map, for this I should draw a corner map, for this I should do a corner map. and then each of them I should simplify to the minimum form and then draw the circuit out of it. So, this would be KMF for E0 would be what? This is, what is that? B0 bar. Did you have to do this? You look at this. You need not have done this exercise because you look at B0, you look at E0, every B0 entry is complemented in E0 entry. So, B0 is E0 bar, is, you do not need an Einstein to do that, right? Right. This is the map for A1, B1. So, again it is E1. This is B3, B2, B1, B0. More time is drawn by writing the map than the actual simplification process. So, I now have to take the second entries here 1001, 1001, 1001, 10, right. Now, this should be, I have two terms because this 4 I can combine as 1, this 4 I can combine as 1. This is the beauty of the don't cares. I use these two don't cares, this don't care, I use 3 of these don't cares, and we don't worry about the other 3 don't cares, we don't care about the other 3 don't cares, right. So, this is where the advantage of don't cares, use it to your advantage, otherwise ditch it, that is what we do all the time, right. You want something from somebody, use it to advantage, and if you do not, forget about that fellow. So, we are teaching you to do it. Okay, what is that now? E1 would be B1, this is B3, B1 B0 bar, B1 bar B0 bar, or B1 B2, B1 B0. I do not know if you remember this. What was that? As a gate, we wrote a X NOR. It is also called now the third one we will draw here. Zero. Now the third row, third column, E2 column has to be written. This is the map for E2. To map 0 1 1 1 0 1 1 1 1 followed by 4 zeros 1, rest of don't cares. This is slightly more involved. These 4 form a group. This 1 1 1 1. This one, this form a group. Second group. Even though there is only one left uncovered, I can use this and this to simplify the logic. And finally, this one has left, so I will have to put it. So, there will be 3 terms. One term consists of this, second term consists of this, third term consists of this 2. So, that will be E2 will be, first we will take this would be B3, B2 bar, B0, then B2 bar B1, this is equal to sign should not be mistaken. And finally, this entry is B2 B1 bar B0 bar, B2 B1 bar B0 bar. Third one. Any questions? Anyone who doesn't follow what is happening here? Fairly straightforward, but still you have to understand what you are doing. I am trying to put together a practical way of using whatever you have learned till now, and this is a useful circuit. Binary to excess-3 converter, binary to gray code converter. These are used in a lot of this logic that big digital machines, computers and all you see. Someplace something will be happening like this and will be part of the whole system you are building later on. And then the last map will be for E4. E3 map, I am sorry. E3 map this will be 3B2, 1B0. First 5 zeros, then 5 ones. Rest I don't care. Is that right? So this can be one big thing. Okay. I think I need to do 2 more terms, right? This and this. Yeah. E3 would be then. E3 would be. This is first we will take this 4. This is B3 B2 bar. B3. Pardon? Yeah, it is B3. It is 8. It is 8. Thank you. B3. Then this will be B2 B0, B2 B0 and B2 B1. So these are the 4 equations, the simplified equations which will form the converter inside this block. So we give B0, B1, B2, B3, BCD values, that is the decimal values written as a binary, and they get converted using these logic functions to get E0, E1, E2, E3, and we get an XS3 code which can be used in processing the computer. At the end you have to go XS3 to BCD, go back, get your original BCD numbers. So the circuit can be drawn easily. E0 is B0, so we have assume that all the B0, B1, B1, B2, B3 and their complements are available to avoid the having to draw inverters. So I will assume that B0 is available. So B0 bar is same as E0 bar. E0 that is first one. E1 will be B1 and B0. I am not showing that B1, B0 could have been directly taken from here within all that to avoid too many connections. The same B0 we are talking about here, this B0 bar is same coming from the same B0 here. The next function E2 is B2 bar B0, B2 bar B1, B2 bar B1 B0 bar. B2 B1 bar B0 bar. All of them together will be put into an OR gate. This is my E2, E3 is finally B3, B2, B0, B2, B1. So, of course, all of them will be in one place and then all these connections are same. For example, this B0 is same as this B0, this B1 is same as this B0. So, you can take one B0 and take it like this. So, the connection will be a little bit confusing and complex. So, I thought you will just understand. You represent like this a solid when you wire it up, of course. There is a B0, B1, B2, B3 coming into a circuit and you have to get them inverted if you want. B0 bar, B1 bar, B2 bar, B3 bar. So, you will have 8 B0, B0 bar, B1, B1 bar, B2, B2 bar, B3, B3 bar. Then you have all these gates, wire them up, crisscross and then get E1, E0, E1, E2, E3. Then the circuit is built. Then you go and give different codes and verify whether corresponding codes are coming as accessory codes. This is a simple procedure with a standard circuit which is a commonly used circuit. It is also easy to understand circuit. All code converters are designed this way only, there is no specific. So, what I am going to do now is to, are there any questions at all? So, what I am going to do is to give you a grey code. What a grey code is, we will draw the, I will tell you what a grey code is and we will draw the truth table and then you follow the same procedure. I leave it as an exercise. Follow the same procedure to get the converted code, that is binary code I will give you, grey code I will give you, the truth table I will give you. From the truth table you get the values for the 4 values of the grey code using the Boolean reduction technique using K maps, then draw the logic. So, I will give you the table and the result. You have to draw the graph and verify my results are correct, okay, and the results are wrong, that means you have done something wrong because I am going to give you correct results, okay. So, let us talk about grey code converter, binary to date. Now, this time I will do binary to grey code, not BCD2. As I said, grey code has been designed to reduce the switching activity. That means from one code to the one binary value to the next binary value, there should only be one bit change. The grey code for a binary number is given a grey code, given a grey code for a given binary number. The next binary number if you take, the grey code can only change in one place. So, one of the zeros can become 1 or one of the ones can become 0. So, there can only one 0 to 1 transition between a grey code of a binary number and the grey code of the next binary number. That is the definition of a grey code. That is the characteristic of the grey code. That, as I said, to reduce the switching activity when you are going counting sequentially, to reduce the switching activity, thereby increasing the speed as well as reducing the power consumption. So, how does it go? So, we will do full binary in this time, not only BCD. So, I will call it B0, B1, B2, B3 again. Zero, 0, 0, 1, 0, 0, 1, 0, 1, 1. I will put 4 at just to make sure I do not make a mistake. There is no significance for these lines. When I write the code, there should be, I will not write it in the, something like help me to put it properly. Oh, one. So I will call this G0, G1, G2, G3. Spelling of gray is this, Gray, gray code, after name of the person, not the gray color. Okay. So we will do this. This is very easy to write, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. Next code will be 0, 0, next bit will be 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0. G2 will be 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. G3 will be 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. This is binary values of the equivalent decimal values from 0 to 15 for 4 bits. You can do it for any number of bits. This is the, earlier I said BCD. A BCD means 0 to 9. So rest of them don't care. Here is a binary I am saying. Just because I stopped to 4 bits does not mean that gray code supplies only 4 bits. Suppose I have a 7-bit binary code, I can get a 7-bit gray code. The same rule will apply, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 3, 4 zeros, 2 zeros, 2 ones, 4 zeros, 4 ones, 8 zeros, 8 ones, 16 zeros, 16 ones, like that you can go on writing. That is why I am calling it a binary to gray code conversion. Even though we are restricted to 4 binary digits, bits, does not mean you cannot do it for 5 bits or 6 bits or 7 bits or 8 bits. So that is the property. You can see now between one number and the next number there is only one position. For example, there is only one change here. You see anything? For example, this 7, here it is 7 to 8, 1, 1, 1 becomes 0, 0, 1, 0, 0, 4 changes. Whereas here is only 1. There is a 1 here, 0 became 1, rest of them. Only one bit has changed from the one position, one number to the next number in a gray code. So I am not going to draw the corner maps. It is your job as an exercise. I am going to give you the answers though, so you can verify this at home. G0 would be B1 exclusive OR B0, G1 would be B2 exclusive OR B1, it's very simple. G2 would be B3 exclusive OR B2, and G3 is same as B3, as you can see, 8 zeros followed by 8 ones, 8 zeros followed by 8 ones. Now you can very easily draw this B0, B1, this is G1, G0, G1, G2, G3. Very simple circuit, 4 exclusive OR gates. Of course, exclusive OR gate you won't read, when you read a corner map you know you will get sum of products and you won't get exclusive OR, but you can simplify it into exclusive OR. This simplification is so easy, when you, this term would be, for example, it will not come like this, it will come as like this. You will get like this, but you can see it as an exclusive OR gate, because you won't get this direct expression from the corner map, because corner map will get the minimum sum of product expression. So this is a sum of product expression. So this has to be converted. You will have to see that this is same as this, sort of connect it up properly. So with 3 exclusive OR gates, I can get a 4-bit binary code into 4-bit gray code. The same logic. If it is 5 bits, one more exclusive OR, B3, B4. It goes on. So 7-bit binary code if you have, you can get 7-bit exclusive OR gate, 7-bit gray code by using 6 exclusive OR gates. It's a very simple, elegant circuit, practically used also. As I said, many times people want to convert digital design, convert the binary code to gray code before doing the processing for all the switching activity and all that I told you, and then get back the binary. So this is a very elegant circuit, commonly used circuit. So you can verify this using Karnaugh. All I am asking you to do is to draw the Karnaugh for each of these values G0, G1, G2, G3, simplify it in this form. From this is evident, this is the same as this, and then this I have already given you. So these are examples of code conversion as one class of circuits. You can go on anything, as I said in the beginning of this course. Anything you see is digital these days, so you can think of applications where lots of inputs and lots of outputs, there may be lots of inputs and one output. Whatever it is, how are they connected? What is the logical connection between the inputs and outputs? Express it very clearly in words. Formulate it as a truth table. Draw a functional block diagram. Draw the truth table, write the truth table, get the map, do the simplification and draw the circuit, get the gates, go to the lab, wire it, measure it and test it. That is the simple design procedure of a digital system, and I showed you with 2 simple examples which are practical examples. We will see some more examples in the next lecture, and finally we will go into the arithmetic circuits which are the basics of computers. Before that, I will give you one more thing which probably can be thought of as another homework. This is one of the assignments. Second assignment, because I don't want to go on drawing the same type of thing again and again. You can do a reading assignment of codes. Any standard digital book will have a codes, a section on codes, Ascii code, XS3 codes, binary code, weighted code and all that type of code. You can take any of those codes, they will give you the binary number and the corresponding codes. Just take any one of them and convert it into this logic. That can be an exercise for you. Then one other thing I want to talk about is the parity generator. A parity generator is something like a, I want to explain what the parity generator is. We will probably see an example of it later on. I send data, digital data means what? Zeros and ones. So constant stream of zeros and ones coming across, if the digital telephony, the digital transmission, internet traffic, ISDN, whatever you name, your digital data that is coming over the transmission lines, and then at the receiving end you get these zeros and ones and try to make sense out of it, because you know the codes, you decode it and find out. But there may be errors occasionally. A 0 can get converted into 1 because of some static. A low level, because of a static, suddenly can become 1. 1 bit instead of 0 got corrupted and was received as a 1. Similarly, a 1 was, because of some drop in the level of the voltage, suddenly 0. So there can be an error of a 0 become 1 or 1 becomes 0. This can happen several bits also, but if only 1 bit is an error, we can see if there is an error in 1 bit by checking what is known as a parity. Suppose I have a bit stream, the number of ones in that bit stream is called the parity. Let us say I am sending a 4 bit at a time. I say I will give information 4 bits at a time, packets of 4 bits. So I will say 1 0 1 1. So 4 bit stream, it has 3 ones. So this is called odd parity. The number of ones in the bit stream I am talking about, the 4 bit stream, is odd, I will call it odd parity. If on the other hand it is 1 0 0 1, called even parity. If the number of ones, if the number of ones is odd, it is called odd parity in a given bit stream. The bit stream is previously defined. You cannot just arbitrarily start at some point, end at some point, and say it is odd parity. They will tell you ASCII, for example, if you take an ASCII code, it is a 7-bit code. So in 7 bits, how many ones are there? You will after every 7 bit you have to count the number of ones, see whether it is an odd or even. So the number of bits they are going to transmit at a given time, you should know. If you know that, they can say whether it is an odd parity or even parity. So they will also put the parity along with that. So for example, an ASCII code, 7-bit code, let us say this is my code. Now I will count my ones, 1 2 3 4 5. So an odd parity, I can put a 0 here or 1 here depending on, put a 1 here, say it is an odd parity. So the extra bit I will add to say that I have odd number of ones. On the other hand, if I had number of ones is even, I will put a 0. So I will deliberately add a parity bit to my bit. So instead of looking at every 7 bit, I capture 8 bits at a time. 7 bit is ASCII, 8 bit is the parity. I verify whether the parity bit checks with the number of ones. If the parity bit does not check with the number of ones, then I know it is an error. So this is one of the techniques, simple technique of detecting simple errors. So first we have to generate this parity, add it along with the bit data stream and send it. When you receive it, you receive the whole thing, count the number of ones and find out the parity bit. If the parity bit matches with the given parity bit, it is fine. If the parity does not match with the given parity bit, then you know, first you can say it is an error, so you can at least ask them to resend it. There are several techniques of error detection and error correction, and then if more than 1 bit is an error, what will happen? If 2 bits are an error also, all those things are there. I am not talking about the error correction code, that is a big topic by itself in communication. But you can do simply, quick check and tell you there must be an error, please send again. Simplest thing you can think of. So the next lecture we will talk about how to generate the parity bit. That will be a good example for combinational logic. So we will draw the truth table for a parity generator and implement it. Okay.